Hey, welcome back. Again, thank you, Professor Dave, for doing such a good job introducing us to the concept of work and kinetic energy and potential energy. I love diving into this because it takes, again, everything we've been learning about forces, it just takes it one level deeper, and it's really a neat idea here. So we have work. Remember, if you don't move anything, you have done no work. You can push on a brick wall all day. Now let's take a look here. What I was looking for you to get in this fill in the block, and maybe it wasn't very clear, but in this block here, I was trying to get you to say that potential energy, PE, is equal to mass, gravity, and the change in height. And over here, I was trying to get into the fact that you can also have potential energy. It's stored in a spring. So you can have spring potential energy. So it's one half the spring constant, and that's unique to each individual spring, like a slinky versus a spring that you might have on a trampoline, times x to the second power. And again, this is called the spring constant, and it is unique to each and every material and spring that there is. And then we went through kinetic energy, we went through the work energy theorem, and if work is positive, then work was done on the system. If work is negative, it was done by the system. When you lift something up, you're giving it potential energy because, well, it has the potential to hurt more if you drop it. That's kind of how I think about it. Like, I would rather drop, my keys on my toes from 1 inch away than drop my keys on my toes from 6 feet away because ouch. And then hopefully you were able to work this problem out. And if you were not able to, you could follow his example there. And if not, just let me know. We'll go over it together. Now let's go on and try some on our own. All right, this is the third time that I've redone these notes, but I have my husband here.
Hello.
And I wanted to approach this a different way than I had in the past. And everything that we've gone over so far still holds true. But in general, the amount of kinetic energy that you have in the beginning, and that's like motion, plus the amount of potential energy, we represent that using a U. I don't know why we just don't use PE, but a lot of times you'll see it as a U. So we're going to use a U.
Okay.
Okay. And this one right here, this potential energy, I stands for initial. This one is going to be due to gravity. And then sometimes we also have a loaded spring. So far, so good?
It says spring, but okay.
They're better?
Mm-hmm.
Okay. I'm actually going to put that as a little subscript, and I'm going to pretend like I don't lose my little...
Mm-hmm. You're doing great.
I know I am. Hold on. Okay. So all of like the energy that you have at the beginning of a situation, plus if there's any work being done on a system, that will always equal. So if like you add energy, you add that in, or if you take away like friction, it would be negative. Okay, stick with me.
Mm-hmm.
By the way, work is always force times distance, cosine of the angle between the two things.
That's what I thought.
Good. All right. That will always equal the final kinetic energy plus, you want to take a guess?
Final.
Gravitation, like
what's... the gravity. That's
potential. Plus the, I'm winning. I should say final. My bad.
Mm-hmm.
Plus the final energy of like being in a spring. So far, so good?
So far, so good.
What do you think about this equation?
It's a lot of letters.
That's right. You know what I am going to do? I'm going to teach these kids if they don't know. We're going to do FD cosine of theta above that. That look okay?
Sure.
Okay. So energy at the beginning
plus
any work done is energy at the end. Okay. I'm going to swoop this stuff together. We are going to group it. And we're going to save this because we're going to use it on every single problem. All right. Are you ready? I got all these problems from this guy. He's my favorite YouTuber.
Favorite?
Yep.
That seems like hyperbole.
Okay, now talk.
Favorite?
Here we go. Ready? How much work is required to stop a 1,500 kilogram car moving at a speed of 125 meters per second?
Does that just say 25 meters per second, not 125 meters per second?
Yeah, didn't I say that?
You said 125.
My bad. Okay, so the initial kinetic energy, is it moving at the beginning?
No. I don't know, is it?
It is moving at a speed of 25. Okay, so we use 1/2, they've already learned this up above,
the initial velocity squared. That's kinetic energy.
Okay.
It didn't say that it was like floating or it was going to like roll
Gotcha.
off a ramp, so we don't have any gravitational.
Mm-hmm.
There's no springs in this problem. However, it does say that there's some work that's going to happen because it says how much work and we're going to stop it. Now, if we're going to stop it, let's talk about this. What do you think? 1/2 mvf squared.
Okay.
What do you think we'll put in for v?
0.
Yeah. And again, it's not like on a ramp or anything, and it's not a loaded spring. Ready? So now all we have to do is fill these things in.
Got it.
Okay, bring this down. You ready? So it's going to be 1/2. What's the mass of our car in kilograms?
1,500.
Okay. What's the initial velocity of our car?
25 meters per second.
Good, and that says kinetic energy says to square it.
Okay.
Plus, we don't know what the work being
That's what
done
we're
is.
looking for. Mm-hmm.
And what about 1/2? What's the mass of the car?
1,500.
And what's the final velocity since it comes to rest?
0.
All right. Now, how good are your algebra skills?
So.
Okay, so I want you to take that to the other side and solve for work. I think their algebra skills should be good enough. They should get. By the way, that should be your answer. I expect all my students to be typing it in. I'm giving my husband enough time to type it in.
Uh-huh.
He's typing in his calculator.
It?
Good, yeah. It would have been when you take it to the other side
negative.
though. Negative 468,750, and energy's measured in joules. Good to go?
How you spell joules?
Joules.
Oh.
Now, what do you think about the fact that it's negative?
What do you mean?
The work being done is negative.
I'm going to say it's directional.
It's not directional, but that's a great guess.
It's against.
Well, how about this? It's slowing down.
Yeah.
So, is it adding energy or subtracting energy?
Subtracting.
Yeah, energy away. So I think, does that help you make understand? I'm not going to do significant figures. They know how to do that, or significant digits. I'm just going to move on.
But where's that energy go? Because energy is neither created nor destroyed.
Well,
so when you take
this one
that
would be
energy
like in
away,
friction. They
where
didn't
does
say
it go?
what it goes into friction, which is like heat or. Okay, let's keep going. We'll get into that in later lessons. Stop confusing them. All right, how much work is required to lift a 40-kilogram crate 20 meters high? So I'm going to grab this. I'm going to grab my sticker that I made.
Yes.
Are you ready to fill this in? Oh, dear.
Yes.
I told you I was going to grab it, and I didn't. The kids are both sick downstairs. This is how much we love you guys. Well, at least me. I'm not sure about him.
I don't know you, but I kind of like
he's
you.
here. He loves me, and that's why. All right. Is there like speed or anything given to us?
Speed?
Yeah.
Yeah, because it's resting.
Okay.
No.
So initial energy would be 0, right?
Yes.
Okay. So no.
Oh.
Is there like a height or anything associated maybe with it?
Well, they want you to get it to 20 meters high.
Okay, so let's
Doesn't
go
take-
ahead and let's talk about that.
We're going to assume that it starts at like
That's
0.
Yeah, we will. We'll put in a 0 though. So since we're talking about like vertical motion, we'll go ahead and pretend there's like. Okay, really, we know this is 0. We know this is going to be 0 too, because h is 0. No springs, and it does say, hey, we're going to be doing some work, right?
Yes, we all love that.
Now, you're lifting it, and then you stop lifting it, so really no kinetic energy at the end, right? That would 0 out, because again, your velocity would be 0.
Right.
But we will have some mgh happening here and no spring.
Yes.
Ready to solve it?
Yes.
What goes in for m?
Mass, what is that? 40 kilograms.
What goes in for gravity?
9.8 meters per second squared.
I didn't even tell them, guys. How high is it initially in the air? We assume we're lifting it from the ground.
Oh, can we assume that? 0.
Okay. Plus the work being done equals, again, what's the mass?
40 kilograms.
What's the gravity?
9.8 meters per
And
second squared.
how high is it at the end?
20 meters high.
All right. Do your algebra and tell me how much work was done.
Oh my.
Remember, this like zeroes out, right?
Whoa.
So essentially just what is that? He's got his phone calculator, guys. He should get that
Did I get
number.
that? 7,840?
Yes, you did.
Wow.
7,840 label.
Work is done in joules.
What do you think
Is that
about
a
it?
J?
Yeah, it's a cursive J.
That's a G. You wrote a
Oh
G.
my gosh. Is that better?
Yeah.
What do you think about the fact that it's positive?
So energy was added.
Yeah. So
But where
we're
did it
okay.
come from?
His work.
From his biceps or
Yeah.
her? Is it a him?
It doesn't
Does
matter.
it say? Oh.
Right. Energy
Could
was
be-
added
could
to
be
the
you
system.
lifting it
Hey,
or
I have
me
a
lifting
question.
it.
Would you rather have a box hit your foot from 0 feet in the air or from 20 meters in the air?
That would be 0.
Right, because in
It
20
doesn't-
it has more energy if it comes from 20 meters
Right.
up, right?
Right.
Okay, thank you, physics. Again, not going to worry about significant digits right now. They can do that on the homework. How much work is required to stretch a spring from 25 centimeters beyond its natural length? Okay, here we go. You ready for my formula?
Mm-hmm. Ready.
Okay, let's do this. All right, we're going to start at 25 centimeters beyond its natural length. We're going to go 85 beyond its natural length. So it's like if this is the natural length,
We're gonna start 25
it's actually
beyond.
like here when it starts, and then it's going to go to like here. Make sense?
Yes.
Okay, I'm just going to like
Okay.
shrink that down.
Yeah. Get that out of the way.
Okay, now, there's no like movement, right? There's no like velocity at the beginning. It's just like it's already
Right,
there.
It's already, yes.
Okay, it's not saying it's like in the air, but we
Right.
definitely have a spring, right? A loaded spring. So it's 1/2 the spring constant, and how far, I'm going to use delta x, how far away it is from its natural like resting position,
Okay.
and that's its initial.
Uh-huh.
There says there's work done, so they want us to figure it out. Does it say it's moving at the end?
New.
No, we just kind of assume like it's being held. It's not in the air. It's not like a vertical spring. And then here we go again. Final is 1/2 kf. How about delta x? Because that means like how far away from its resting spot it is.
Okay.
Ready to fill things in?
I think so.
Okay. So 1/2. Did it say what the spring constant was? Yes. Look at the very end. The spring constant. It's how many
okay.
Newton meters it takes.
500.
How many? It actually means how many newtons it takes to move it 1 meter. All right, now the very beginning spot. See how it's 25 centimeters beyond its natural?
Yes.
What is that in terms of meters? We have to go to meters.
What is that? Wait.
I know you can-
0.25?
Yes. So it starts at 0.25 away from its natural state.
Uh-huh.
Some work is done to it. And so we're going to stretch it some more. What is 1/2 the same constant? Doesn't change for the spring. What's its new distance away from? Do you remember?
Is it 0.85?
Yeah. Okay, so I'm just going to move that over so I have a nice looking thing. Okay, now I need your algebra to be good. You ready?
Yeah.
Okay, grab your cell phone.
Mm-hmm.
My students should be doing the same thing.
Mm-hmm.
Okay, all you need to do is take this guy over to this side using subtraction. Okay?
All right, let's see.
And you
here.
should get that. Go
Let's
ahead,
see.
type that puppy in there. Yep. However you guys are typing it in, please do that, okay? I expect you guys to be able to do that
Oh,
too.
my algebra was not.
Oh, your algebra is a little faulty.
Hold on.
Do you
Hold
need-
on.
Do you
hold
need
on.
me to step in?
No.
Are you sure? Let's have a race. You're done.
Is that?
No.
Oh,
So like
okay,
that,
what
and
am I
then you
not
have to do
doing right?
minus. I'm not sure.
What am I not doing right?
So what I typed in on the calculator is this.
Wait, you typed that? I was typing this one in.
Why no? But you have to. Oh, you have to start with this and then subtract this.
Oh, that.
Well, I'm sorry.
Oh, nope.
My
Okay, restart.
Well, it's okay because I got it now. I mean, no offense.
Mm-hmm.
I got 165,
Let's
which,
see.
by the way, is the right answer. Now, what do you think about the... You're still typing.
Mm-hmm.
I thought I went...
All right.
Okay.
Whatever. What is
Oh,
that?
that's for Rosie's medicine. Okay. What was I doing?
I don't
Oh,
know.
what about the fact that it's positive? Can you picture N or G added? Like, if you were to stretch a spring or a rubber band further,
Yes.
does that make sense? You're adding energy, like potential energy. Like if you stretch a rubber band further and snap it on someone, it has the potential to hurt them more.
Yes.
Okay, so are we happy that energy was added?
Yeah, it must have come from the person's arm then when they pulled it. That's
Yeah.
where
It
came
was the
from.
effort of the human.
Ah.
Good. Okay, a 15. Yes.
Was this the last one?
Uh-huh. A 15 kilogram block
This is a lot of words.
slides on a horizontal surface. Whoops, sorry, I'm sick. With an initial speed. So it has a speed at the beginning. So when we hit play, we see that puppy moving. It's sliding. The
Why are you
speed of
sliding
the...
a puppy?
It's not. It's a block. Don't distract them. The speed of the block is 7 meters per second after traveling a distance. So it's going to go a distance, and then the speed's going to decrease to 7 meters a second.
Okay.
So this is initial. This is final.
With you?
250 meters. That's a lot. How much work is done by friction? Because nothing else is touching it except for friction. Are you ready?
Ready.
Watch my magic formula. I just
I have a
love...
quick question.
Yeah, how can I help you?
Maybe you need to... I don't know. But when I see that, I think
Yeah.
KFC. Like Kentucky Fried
I
Chicken.
really wish you hadn't done that. That's okay though. I mean, like now they're all. That's good. Hey, if they like it. I'm sorry, I was so negative.
Okay.
Okay. Does it have a movement at the beginning?
Yes.
Okay, so we're gonna keep. I'm changing to red. I don't know why. What color do you want me to use?
I don't know. I'm thinking about fried chicken now.
Okay, brown then. I mean, chicken's brown. That's disgusting. They're gonna hate that. And is it like lifting up in the air at all?
It's going sliding.
Okay. Is there a spring?
No.
There is some work being done.
Friction.
That's right. Yeah, and we're gonna have. This is weird because the last question's kind of tricky. Is it still moving at the end of our problem?
Yes.
Yeah. So we are gonna have a 1/2 mv/f squared. Is it in the air at the end of our problem? Like, is it a roller coaster? Okay. No. What about a spring?
No.
Is it stopping on a spring? No.
No.
Okay. It could be. Eventually, it will be, but we're just warming up. It bothers me that that's not brown.
Then change it.
I am. Okay.
Look at you.
So just to make it look better, I'm going to kind of squeeze that stuff in and focus. You ready? I have a student right now. He zooms in as much as possible and he writes like this big. And then when I grade it, this is what it looks like. And I'm 39 years old. You know who you are. It's okay. You watch your notes, so just know that you will forever be in my notes. He's a good boy. All right, let's get rolling.
I'm not the one talking.
Oh, I'm so sorry. 1/2. Boy, I really hope he hears that shout out there. How big is the mass?
What's it say over there? 15 kilograms?
What's the velocity initially?
Is it 18?
Mm-hmm. We don't know the work done, but maybe I'll actually just write the work of friction. Does that look better? You like that better? Okay. My bad. 1/2. Is it, what's the mass?
15.
And the velocity at the end?
Is it 7?
Yeah. All right. I would let you write this problem out, but your handwriting's atrocious.
Mm-hmm.
Kind of like some other kids in my class. Ready? Let's practice your algebra. Just do better this time.
Uh-huh.
See, guys, I'm just as mean to him. Not in a mean way. You just need to do a little better.
Just do better?
It's okay. Yeah, I mean, we all need to do
Just
better.
do better.
We all need to do better in different ways. I mean, I'm perfect, but I'm definitely not perfect. Nope. Okay, so what was the work of friction? What do you think? Are you going to go positive or negative while you're thinking? Typing in. He's typing it in his cell phone calculator. Just so you guys know, I'm not just playing with the screen here. I mean, I am, but just waiting.
Is that the right answer or not? Did I do it wrong?
Oh, you know what? No. That's me okay. I think you're okay. Let me go back.
Oh, my.
I've redone these notes like 7,000 times. Is that what you got?
Where?
Yeah. Okay, that's good.
Ooh, I got it right.
Okay, so on your calculator, you got negative 2062.5. What do you think about the fact that it's negative?
I'm going to go back to what you told me earlier, energy being taken away.
Yeah.
See how I remember things?
Yeah.
And it went away in the friction. The friction ate it up.
Yum. Okay. How much work was done by friction? There it is.
Could a woodchuck chuck if a woodchuck could chuck?
That was so distracting. Calculate the average frictional force. Woof, you ready for this? Well, here's what we know. There's part A.
Another part? Oh, my goodness.
So we need to know the average frictional force.
Uh-huh.
Well, you need to know that work equals, any work will always equal the force of that item times the distance the object moves, cosine of the angle between them.
Cosine?
Okay, question.
Why not sine or tangent?
In our picture, which way is the distance? It's moving from left to
right.
Okay, so here's the distance. How would friction oppose that to the
left? How
So
do we know
what's-
that it's not going the other way down a hill this way?
It really wouldn't matter because if
Oh.
one was going left and one was going right, guess
So
what the
then it doesn't
cosine?
even
Guess what
matter
the
then.
angle would be between
Doesn't
them?
even matter then.
Well, no, because the angle is 180 between them. See, boink. Okay, so watch this. So the work of friction. Actually, let's replace that with our number, shall we? Again, guys, you'll do significant digits in your final answers. I just want to get this done for you, okay? Equals. We're trying to figure out the force of friction. That's what the problem said, right?
Oh.
Am I doing okay?
Mm-hmm.
Times the distance it moves. It did tell us what was the distance it moves.
Oh, 250 meters. That's
That's right.
Yes.
And remember, what did I say about the angle between those two?
180.
That's right. Here's what you're going to do for me, okay? You're going to take this number
Yeah.
and you're going to divide by 250, and then you will divide by cosine of 180. Those are your algebra skills.
Oh no, my number went away.
And that's unfortunate. I mean, you
I
can
don't even
literally
remember
just
what my
type it
number
in.
was now.
I need you to type it in though, because I only have the final answer for part C. Look,
Alright.
I'm done.
2
2.6. Yeah, that looks good.
divided by.
Good. Again, hopefully you guys are also typing this in your
divided
calculator.
by- Oh, how am I supposed to do cosine?
It's right here. You just hit the little
Where?
down arrow. Uh-oh. Hit that down arrow and then cosine. There you go.
Oh.
180.
How about that? I learned something here.
Okay,
Is that
so
it?
negative 13.7854 essentially. Now,
Wait.
what's up?
I didn't put a negative
You
sign
didn't
in
put a
there.
negative sign here. That should be positive.
Yeah, I didn't put a negative sign in the 2000. Yeah, I just.
Okay, yeah. I was going to say you definitely should have got a positive because forces,
Yeah,
we're just saying this
yes,
is the
yes.
force. It's not asking for direction. Okay.
That's why.
I just need to double check that that's right. Did that what I got? Oh dear.
All right, let's try it again.
I'm not sure if you typed that in right, dear.
Okay, let's try it
Oh
again.
dear.
What is it? Ready?
It's okay. Maybe I'll edit this part out.
Why?
Because sometimes they quit on me.
Human error.
Okay, go ahead. Negative 2062.5
0.5.
divided by 250 divided by cosine of 180. There it is. It's okay, honey. We all make mistakes.
Yep.
Oh, do you know what force is measured in?
Newtons.
Yep. All right, so that's part B. Again, significant digits they should be able to do. Part C, wanted to know
What did part C want to know?
what the coefficient of kinetic friction between the block and the surface is. And now we go one step further, okay? They should remember from previous studies, especially their last test,
Of course.
that the force of friction is the coefficient of kinetic friction times Fn. Oh no. They should be thinking, ooh, I need a quick little free body diagram. Here it is. Okay, here's your block. Do you like it? Here's the normal force.
Your lines are a little
Here's the
angled there.
weight. Here's friction. But for me to get normal force, I would do like the F net Y's equals a positive Fn minus a W. They're not moving in the Y direction. This they know how to do. Minus mg. So Fn would equal, because there's no diagonals and there's no ramp, mg. What was the mass? 15, 9.8. Where's your calculator, dear?
Right here.
Let me have it.
What?
I just want to know what 15 times 9.8 is. This hopefully is something they remember
Close
how to do.
150, right? Yeah,
147. Okay, so now I'm going to go right back up here. Do a quick duplicate. Guess what I'm going to replace Fn with?
I'm going to guess 147.
And guess how you can solve for the coefficient of kinetic friction?
Magic.
Divide. Go ahead, let me hear it, because this
Divide what, 8.25 by 147?
is and this is a Newton, so the units cancel out.
Whoop, whoop, whoop. Is that?
You got it. Yep. And that's all there is to it.
That's it. Easy peasy, huh?
So I hope that that little equation was helpful for them. I mean, it's massive, but like if you can pick out what you have and what you don't have. One more thing I need to tell them. I'm really hoping that they're holding on. If a problem asks you for the work done by gravity, it's not asking the work done to the system. It's saying what's the work of gravity, because there's a lot of things that are working in the system. They just do like the UF minus the UI. Like they'll do like mg last h minus mg initial h. Just wanted to say that on there, okay, guys? So if it says, hey, what's the work that gravity performed? Just find your two separate potential energies and subtract them. So it's not like an extra force on the system. They just want to know what was the work of gravity specifically.
I think doing physics
One more
with
thing.
KFC would be better.
One more thing. Since work is this equation, if a problem tells you the force and the distance and the angle between them, you can just use this formula to figure out what the work done to the system is. So you don't have to do the big long formula.
How about that?
All right. Tell them goodbye.
Goodbye.
I appreciate you. I even love you.